Hi, this is your video for section 5.5. This one is about some new identities called the double angle identities. And the reason we call these double angle identities is that in each one, what we have inside of our trig function is 2 times an angle. So we'll have one identity for the sine of 2 times a, and then for the cosine of 2 times a, we actually have 3 different forms of the identity. For the one for sine of 2a, is just 2 times sine a cosine a. For cosine of 2a, the first one is cosine squared a minus sine squared a. Another form of this is 2 cosine squared a minus 1. And a third form is 1 minus 2 sine squared a. For cosine of 2a, you can use any one of these 3 forms. Which one we use is going to depend a lot on what we're doing and what information we already have. Now let's look at an example of using some of these identities. In this problem, we know that the cosine of theta is 3/5 and the sine of theta is negative 4/5. And we're going to try and find exact values for sine, cosine, and tangent of 2 times theta. And then once we find those, we'll be able to determine what quadrant 2 theta is in. So let's start with sine of 2 theta. We're just going to go back to our identity up here. So instead of an a, we're going to have a theta. Sine of 2 theta would be the same as 2 sine theta cosine theta. Now since we have both of these values, we're just going to plug those in. In place of sine theta, we're going to put negative 4/5. In place of cosine theta, we're putting in 3/5. And if we multiply all of this out, we're going to get negative 24 over 25. One thing you can always check with these kind of problems, if you're doing sine and cosine, remember that sine and cosine always have to be between negative 1 and positive 1. So if we had gotten something here that was bigger than negative 1, then we would know that we had done something wrong. Now we're going to find the cosine of 2 theta. For this one, we would have our choice of any one of these 3 identities, but since we have both sine and cosine of theta, I'm going to just use this first identity. I put the theta in there instead of the a. That would give me cosine squared theta minus sine squared theta. Now remember, this is the same as cosine of theta squared, and this is the same as sine of theta squared. Now I'm going to substitute in the values that I have. Cosine of theta is 3/5, and sine of theta is negative 4/5. And then remember, when you square something, even if you're squaring a negative, it's going to come out positive. So this one would be 9/25. This one, you'd still have the minus here, and then this would turn out to be a positive 16 over 25. When we subtract those two, we would get negative 7 over 25. Now we were also supposed to find the tangent of 2 theta. Now that we have sine and cosine, we can just use our quotient identity to find that. The tangent of 2 theta would be the sine of 2 theta over the cosine of 2 theta. We can put in the values that we already found. That would be negative 24 over 25 and negative 7 over 25. And if we simplify that, we get 24 over 7. There's our tangent of 2 theta. Now the last thing we're trying to find is the quadrant of 2 theta. Both of these are negative, and then our tangent is positive. The quadrant where tangent is positive and everything else is negative would be the third quadrant. That means that 2 theta is in quadrant 3. Let's look at another example. This one, we know that the sine of 3x is equal to negative 7/9. And we're trying to find exact values for the cosine of 6x and the cosine of 12x. Well, let's start with the cosine of 6x. If we compare the angle we have here to the angle we have here, this is actually the double of this angle. That's why we call this the double angle identity, because we're taking the angle and doubling it. So if we think of this one as being a, then 6x would be 2a. we want to go back to one of our identities for the cosine of 2a. Now what we want to do though is choose which one will work based on the information we have. What we know is the sine of a. Let's pick the one that only involves the sine of a and doesn't involve the cosine of a. So that would be number 3 right here. We're going to use this identity, and now in place of the 2a, I'm going to put in 6x. In place of the a, I'm putting in 3x. And again, the sine squared means that we're taking the sine of 3x and squaring that. I can substitute in the value that I know for sine of x, which is negative 7/9. When I square negative 7/9, I'm going to get a positive 49/81. And we were trying to find exact values, so I want to keep this in a fraction form. And if I work all of this out, this is going to give me a negative 17/81. Now let's do the next part, which is to find the cosine of 12x. If we look at 12x and 6x, 12x is double of this angle. So we're going to start over. Now if we call 6x the a and we call 12x the 2a, then we want to use one of our double angle cosine identities to find this. But this time what we know is actually the cosine of 6x. So we have the value for the cosine of a. So we want to use the identity that only involves cosine, and that would be this one in the middle. There's the identity we're going to use. This time our 2a is going to be the 12x, and our a is the 6x. Here we're taking the cosine of 6a, that value, and squaring it. We just found out that the cosine of 6a is negative 17/81. I'm plugging that in here. And then I use my calculator to figure this all out and write it in a fraction form since we want exact values. This turns out to be negative 5,983 over 6,561. The next thing we're going to do is use our double angle identities to verify another identity. So on this one, let's work on both sides. The reason for that is on both sides we've got a double angle. So on both sides we want to substitute in one of our double angle identities. On this side we've got the sine of 2x, so there's only one that we can substitute in there. So I'm going to start with this side. Sine of 2x would be the same as 2 sine x cosine x. And I'm going to work on this side in a minute, but first I want to work on this side a little bit just so I can see kind of what I want the other side to look like. The other thing that I could do here is I could rewrite cotangent in terms of sine and cosine. Cotangent is cosine over sine. That would give me cosine of x over sine x times 2 sine x cosine x. And that means that I can cancel out the sines. That's going to give me 2 times cosine squared x. So now that I have that, I'm going to go back to my other side, and when I use an identity for the cosine of 2x, I want to choose between those three. Since I want this to come out with just cosine, I'm going to choose the identity for cosine of 2x that only involves the cosine. And that is 2 cosine squared x minus 1. So I'm taking this and I'm substituting in that. Then if I simplify this, I've got a 1 here and a minus 1. So all I'll have left is the 2 cosine squared of x. And that's actually what I was trying to get to. These two problems have something that looks like the right side of one of our double angle identities. In this one we have a cosine squared minus a sine squared. And notice here the angles are the same. We have the 7x here and the 7x here. This looks like one of our double angle cosine identities. And that is this one. So I've got the right side of this one. This means that I want my A to be 7x. And that means over here, I can put in 7x for the A. And then I can go ahead and multiply inside of here. That gives me the cosine of 14x. And that's as much simplifying as we can do. Do the same thing with this one. On this one, I've got 2 times sine of 15 degrees times cosine of 15 degrees. On this one, just like the last one, the two angles match, so that makes this look like one of my double angle identities, and it's the one for sine. Because sine of 2a is 2 sine a cosine a. Here where I've got the 15 degrees, that's going to be my a. That means that on this side I would have the sine of 2 times 15 degrees. And I can just go ahead and multiply those two. That gives me the sine of 30 degrees. And the sine of 30 degrees, that's one of those special angles that we know the values for. The sine of 30 degrees is actually equal to 1/2. So this whole thing simplifies to just 1/2. We have one more example to do here. In this one, we're trying to write sine of 3x in terms of sine of x. The big thing to remember with these is that if you have a number multiplied inside of here, you can't just pull it out to the outside. It would be nice if it worked that way, but it just doesn't. So what we need to do is figure out what kind of identity we could use to rewrite this some other way. The first one we're going to look at is one of our addition identities. Remember the addition identity for sine looked like this. What we could do is take two expressions that would add together to give us 3x, and we could put those two in here. We want one of them to just be x, because we want to eventually get this down to being in terms of sine of x. So to have one of these be x, we could take x plus 2x. That could be our a plus b. We can plug this into our identity. That would give us the sine of x times the cosine of 2x plus the cosine of x times the sine of 2x. Now we want to take both of our double angles and use identities for those. The thing to remember in this one is that we're trying to write this in terms of sine of x. So here where I have a choice of which identity to use, I'm going to choose the one that only involves the sine. And that would be 1 minus 2 sine squared of x. Now this one I don't have a choice. So sine of 2x is 2 sine x cosine x. Now I'm going to go through here and simplify, and then I'm going to end up with a cosine squared x. I'm going to use another identity to write that in terms of sine of x, so that I have all sine of x in this formula. Here I'm just going to distribute the sine of x. So I have sine of x minus 2 sine cubed of x. And here, if I simplify this a little bit, this is 2 sine x cosine squared x. Now I'm going to use one of my Pythagorean identities. I'm going to rewrite cosine squared x as 1 minus sine squared x. Now I can distribute the 2 sine x. When I distribute it here, I'm going to get 2 sine cubed x. So everything in here now is in terms of sine. One last thing I can do though is I can combine some like terms. These work just like they do in a regular algebra class. So if we have sine of x here and we have 2 sine of x here, those are like terms that we can combine. That would give us 3 sine x. And then here, both places we have sine cubed, so we can combine those two terms. We would end up with a minus 4 sine cubed x. Now this is as simple as we can get it, so this would be our expression just in terms of sine of x.